Digital addition is straightforward to implement by applying our optimization methods for boolean logic and digital implementation. So what is binary addition? Let's take a look at the addition of two simple binary numbers. Let's add the numbers 0, 1, 1, 0 and 0, 1, 0, 1. These numbers are 6 and 5 respectively in decimal. If we were to add our two binary numbers here, we could then look at these using our elementary school arithmetic. We're just using the binary base, so we'll start with this column. 0 plus 1 is equal to 1, and then the carry is equal to 0. We're now in the second column. 0 plus 1 plus 0 is equal to 1. Now, the carry is equal to 0 as well on this second column. Now we look at our third column. 0 plus 1 is 0, and our carry is 1. And then we have output here. 1 plus 0 is 1, and our carry is 0. And so we have a final output, 0, 1, 0, 1, 1. What is this equal to? Assuming unsigned integers for now. Okay, what is this number here? Well, we have 8 plus 2 plus 1 equals 11, so 6 plus 5, that equals 11, and we see it checks out. Well, if we look at these three rows here, what do we see for this 4-bit addition? Well, we see A3, A2, A1, and A0. We have 4 bits of input for A. And if we look at this is for our first integer. For our second integer, we have B3, B2, B1, B0, and we have 4 bits of input for B. Finally, we're going to look at our output here. How many bits of output? Well, we have S4, S3, S2, S1, and S0. Why do we have this extra bit here? Well, let's look here. If we have 1, 0, 0, 0 plus 1, 0, 0, 0, if we add these two numbers together, we're going to get 1, 0, 0, 0, 0. Right? So 0 plus 0 is 0, carry is 0, 0 plus 0 plus 0 is 0, carry is 0, we get 0 again. 1 plus 1 plus 0, 0 is 0, and then we carry a 1, and then we have, this is our output. So we have, at least, we have to account for 5 bits of output for the sum. So this is pretty grotesque when we think about it a little more closely. We can work with 8 bits of input if we're using binary or boolean algebra. In boolean algebra, we have 8 variable equations now. Number of possible input combinations, 2 to the power of 8 equals 256 entries in truth table. That's for 4-bit addition, which is a little bit out of our reach if we're going to be doing this by hand. Typically, processors work with 32-bit, if not 64-bit operations. If we were going to do this by hand directly, using Boolean equations, then it would be 2 to the power of 64 or 2 to the power of 128 possible entries, which is way too much to actually handle, especially by hand. So we need some systematic method for solving this problem. And the trick to handling this is to break it down. 0, 1, 1, 0 and 0, 1, 0, 1. We need to break it down into smaller problems. So we'll say 0, 1, 0, 1, 1. Well, let's look here. If we take this and we have the carry 0, carry 0, carry 1, and carry 0, and we just assume now, if we want congruency, for each column here, they're almost all the same. If we look at a column at a time, then it makes the problem smaller. One column of addition. Generally speaking, 3 inputs, because we have AI, BI, C in I, and we have 2 outputs. The sum, and then C out I. So let's look at this column here. We have 1, 2, 3 inputs, and we have our sum output, and this is our carry output. Notice that an output from one stage is an input to the next stage. What about this first column here, though? What about this first column? We have only A and B. What about the C in? Well, we can assign a constant value 0 here, and now the first column matches all the other columns. And our last column, we have only an output here. This value can be copied to this output value here. So no logic is necessary for the last column. Now that we've broken it down, we can see that we need only one small logic block, or one logic block that is significantly smaller than the 8 input 5 output model, 8 input 5 output circuit. Now we need 1, 2, 3 inputs and 1, 2 outputs. A, B, C in, and then the sum and C out. And this is our addition circuit that we are going to build. So let's try listing the truth table for this 3 input 2 output circuit. We have A, B, C in, and we have C out, and S as our outputs. Let's try extending the table, and let's create the truth table now. So now we just need to add up the number of ones on each row and then give the output here for Cout and S. Notice that the S is the ones column and the Cout is the twos column. So once we add the number up, we can write the number in binary with the twos column and ones column set appropriately. So what is 0 plus 0 plus 0? It is 0, 2-bit value 0. 0 plus 0 plus 1 is the value 1, 0, 1. 0 plus 1 plus 0 is the value 1 again, 0, sum is 1. 0 plus 1 plus 1 is the number 2, 1, 0. 1 plus 0 plus 0 is the number 1 again. 1 plus 0 plus 1 is the number 2 again, 1 and 0. 1 plus 1 plus 0 is the number 2. Finally, 1 plus 1 plus 1 is the number 3. Oops, 2 is 1, 0 in binary, excuse me. 1 plus 1 plus 1 is the number 3, 1, 1. When we have this circuit for building a single column of the binary addition circuit, we need to think, how do we assemble the binary addition circuits for each column into a full 4-bit addition? Well, let's try redrawing our addition circuit. We can have A, B, we'll place C in here at the bottom, C out at the top, we'll place S here. Now we can place 4 of these in order. A input, B input, C in, C out, sum. A, B, C, I, C, O, sum. A, B, C, I, C, O, and then sum again. We have A0 and B0. A1 and B1 as inputs. A2 and B2 as inputs. And then we have A3 and B3 as inputs. Now a carry out on the first column goes as a carry in to the second column. Carry out on from the second column goes as a carry in input on the third column. The third carry out goes to the fourth column, and then we have this here. We now can label sum 3, 2, 1, and 0. So sum 0, sum 1, sum 2, sum 3. Now it's a little bit different from before. We labeled S0 to S4 for the 5-bit, but we can label that as C out here, and we have a CI here. So we now have constructed a 4-bit adder circuit, and this is done with 1-bit adder circuits. If we wish to use this directly in a circuit, we could assign the value 0 to CI, and then CO could be connected directly to our 4th bit out, or our S4 output. Optimizing this circuit here and optimizing multi-bit adders beyond the 1-bit adder, so 2 bits, 3, 4 bits, 8 bits, etc., is a very involved topic of research. Many hours, actually years, have been spent researching this problem, and there's still new material being published in literature about it today even. So I welcome you to take a look at your application for where you wish to implement addition, and then come up with an optimization method for a 1-bit adder or a 2-bit adder or a 4-bit adder as fits your needs.